Hello, my name is Gary Oblonsky.
I'm Bryce Calvetti.
I'm Stanley Moy. So our project is on axiomatic design on deep hole drilling. Our objective is to utilize axiomatic design to create a deep circular hole in a workpiece. And a deep hole drilling is defined as any hole that is more than 5 times the diameter, deeper than the diameter. And some of the issues that occur in deep hole drilling is maintaining large torque transmission along the shaft, quality and surface finish, straightness of the hole, and sufficient chip evacuation to complete the process. And we want this process to be completed in a single pass, just because multiple passes, more time, lose money.
Currently, for deep hole drilling, there's a couple of state-of-the-arts we're going to talk about quickly. One of the main one is Boring and Trade Panning Association. As you can see from the top here, the drill has a hollow center where the chips are evacuated through, and it uses 3 cutting edges along the hole, and it has guide pads on the side. And the coolant is introduced outside the bit and is pushed through the center. Gun drilling is a hollow tube with a V-shaped flute. Picture up here. It ejects the chips along the flute, and it's typically used for smaller diameter holes. And reaming is performed on pre-existing holes for a desired surface finish of the hole. The constraints of our project would be a type of material and the hole specification, which would be decided by the whoever is ordering the hole for whatever application it's being used.
So this is our upper level decomposition for actually creating a deep hole, circular hole in a workpiece. The first 2 FRs, hold workpiece and adjust hold position between tool and workpiece. This was not the scope of our innovation for our project, and these are just basic components that would vary between the type of workpiece. So that would be adjusted depending on what the workpiece is. So the main focus that we had for this particular decomposition was remove unwanted material from the workpiece, and it's actually a whole material removal operation. As I said, our main focus is remove unwanted material from workpiece. Sorry, I got ahead of myself. This is what we broke down the material removal in, and this is what we believe would be C-min for creating a deep hole, or removing a material, I should say. And that's remove bulk material from the workpiece. And we used a drill operation. In particular, we chose to choose a BTA style drill. Remove extra material to obtain desired surface finish. We chose the reaming operation for this. And to control thermal stability of tool and workpieces, some sort of coolant operation. So this is the removal of the bulk of material. This is how we broke this down into the drill operation. We have remove material by chip formation, which I'm really bad at CAD, so this is my awesome picture of a BTA. That's why we decided to show it in the state of the art, because it looks a lot better there, where you have multiple sort of drill heads on there and a hollow shaft in the middle for the chip evacuation. We also added, or our second FR for this is guide drill along a set path, and that's what these little plastic guides are for. So what happens is the outer shaft will be flush against the workpiece as it goes through, and it actually holds the inner shaft in a straight line, which will help maintain straightness, because typical drilling operations, depending on the cutting forces, may slide off on its course and not be within its tolerances. Provide area for chip extraction. That's a hollow inner shaft, which goes all the way throughout, and that's for the removal of the bulk material. And provide appropriate torque is the actual inner shaft.
FR 3.2 is to remove the extra material to obtain the desired surface finish of the hole. So we have it broken down into 4 functional requirements itself. The first part is to remove the remaining material by chip formation. That would be done by a reaming operation used. And this is the outer shaft that you saw previously that was clear in the previous picture. And what this would do is remove very minimal amounts of material left over by the hole from the BTA drill to get whatever surface finish you would want desired by the customer. The second 3.2.2 is to guide the tool along the hole. And we have outer plastic guides, which you can't see on the picture here. It's further up, but they would be similar to the plastic guides on the inside and would be very small and allow the reaming operation to keep straight. Provide area for chip extraction. There's area opening after the reaming, which you can see right here. It's not it.
Just the area that's cut by the workpiece.
Okay, so it's opening after the reaming is complete, and then provide appropriate torque would also be another constraint from the customer, as the material and the hole specifications would be decided by them. Oh yeah, sorry. So easy to see things. Both these shafts are separate and they rotate on their own accord, so you can choose the appropriate cutting speed and loads for each shaft individually. They're not linked at all. So you, for each operation, when you go through, they have their own speeds.
For our FR3.3, we need to control the thermal stability of the tool and workpiece, because at the interface there's heat, and we don't want the heat to go over the tool's critical temperature, or else you have reduced tool life. And for the DP, it was the coolant operation, and we broke that down to 5 childs. So we first want to control the temperature of the coolant, and we decided to use a heat pump, which is not shown in the CAD drawing. And 3.32 is to provide a path for the coolant to enter. So here you see that there are 2 concentric shafts, and between them there is an open gap. The arrows here, this is where the coolant enters into the tool and workpiece. And we also need to provide for the coolant to reach the BTA drill head. And it's here, DP 3.3 shown with the grooves opening. And this, and then we have a 3.34, provide a path for the coolant to reach the reamer. You can't see it here, but because it's transparent. What? Yeah, so this kind of a groove here that would be leading the coolant into the reamer. And we also need to provide a path for the coolant to exit, or else if there's no exit area, then you're going to flood the machine. So the opening, so the this inner shaft here is hollow. So when the coolant comes down, it will go through the inner tube, and that would also push the chips away, so that it prevents clogging.
I guess I'll just talk about our matrix real quick. There was quite a few coupled things in here, such as like the guidance system, where sort of the outer shaft guides directly respond to the inner shaft guides, and obviously you'd need to guide the outer shaft before you'd be able to guide the inner shaft. That's essentially what we had for the major coupling. Everything else was separate, with removing the bulk of material has its own like exit path, and the surface finishing had its own exit path as well. The main conclusion we had was we improved the process creating a deep hole by innovating a guidance system for creating a straight hole, added a reamer for surface finish, and provided a source of 2 different torques depending on the cutting operation. So, like Garrett said, each can have its own cutting speed to complete its particular task. Any questions? No questions. I like it.
All right, I've got a couple.
Right.
Can you back up to that stuff? All right, so you're showing coupling between DP 3.1 and DP 3.2.
Oh, yeah, I definitely forgot to explain that. You need to remove the bulk of the material before you can actually use the reamer to do a surface, so it's temporarily coupled.
Okay. So at this level, they're coupled, the 3.1 and the 3.2. Doesn't that mean that one of these children, which would be in this part of the matrix, should also be coupled?
Yeah, it's no, it's remove remaining material by chip formation. It'd be this guy right here.
And that is coupled with which one of these? So remove, it's got to be coupled.
It's coupled with the drill operation, and yeah, it's coupled with the drill bit for the most part.
With the drill bit.
Yeah.
So
You got to remember
here's the
that.
point.
Put an X there.
We talked about this going the other way. If this is coupled, for example, then we need to see the coupling appearance.
tried to figure it out in the Clara. I had no idea how to make it automatically do it. Unless
Why did you wait till now to ask the question? Since you could have emailed me any time in the last 14
we did
weeks.
email you, but I think we forgot to ask you this. Because we emailed you the decomp, and we probably forgot to.
Yeah, I definitely forgot to ask that particular question.
All right. Well, we have time. I'll show you the rest of it.
All right.
Thank you.
No other questions?
All right.
I have a question about the plastic spacers. How long are you planning on the plastic spacers?
You have to echo the question for this.
All right.
Because when you go to push the material out, to remove chips, the chips get behind the spacers.
Yeah, the question is how big the plastic spacers are on the inside. I think they can see the screen. So this guy in the middle right here. We just wanted enough area for the force to like hold it in place. So they don't even have to be very big at all, as long as it's like essentially loaded. We didn't really, in particular, choose a size because depending on the tool depends on the whole specification of that the customer wants. So we just want, it's like ratioed depending on the size of the hole they want, I guess.
But you're also going to just, you're going to have to reference the size of the chips between the two.
Yeah.
If the chips too big to fit through that hole, you're going to just find the hole.
Yeah.
Yep.
Here you have to
All right. Provide the path for the coolant to reach. Oh, the DP part. All right. Well, the question was is DP 3.3.3 through 3.3.5 all seem to be the exact same thing. They kind of are the same concept, but they're different things in general. Like the pockets in the drill head are this pocket in general right here. So like they're completely independent of the coolant getting to the reamers, because these pockets provide the coolant to get to the reamers, and these pockets provide the coolant to get to the drill head. No, the opening in the drill head's the picture of the BTA, which is this guy right here.
Let's go to that flow.
The flow one.
So how do you independently control the amount of fluid that's here and here?
Size of the hole. Well, yeah.
So where's that in your deep tank?
Very good question.
Okay, so let me make a suggestion here. Say provide path for the coolant. Is that solution neutral?
Not really.
So a better FR might be to supply a certain flow rate of coolant, right? And then here you're going to have something more specific. So just pockets, it's going to be cross-section of pockets.
All right.
So then if you have a certain pressure applied here, right, the flow is going to depend on the cross-sectional area.
Okay.
Yeah.
Yeah.
Okay? So this is a fairly common mistake. So make note of this, right? This is still a learning opportunity here. This is not solution neutral. It anticipates the thing. It's not really getting at what's the functional requirement. Why do I care if there's a path there?
All right.
I care if it's cool. I care if I can remove the chips.